So in this video we're going to look at the following problem. So a bead of mass m slides frictionlessly on the inner surface of a hemispherical bowl of radius r in the Earth's gravitational field. Use cylindrical coordinates r, theta and z and take upwards as the positive z direction. So in the first question of this problem, we want to find the r, theta and z components of Newton's equations of motion, and we're told that these equations will contain an unknown constraint force. And as a hint, we're told to use z equals minus square root capital R squared minus little r squared. So I've drawn a sketch of the situation on the page below, and so we have that z is just minus capital R squared minus little r squared, square rooted, and we want to find the Newtonian equations of motion. And so we know that first to do this we have to find the forces acting on our bead, and we know that there's two forces. So there's the weight and there's the normal force that is exerted by the bowl on the bead. And so the normal force will point in the direction that's perpendicular to the surface at that point. So using this we can write the net force. So the net force is going to be the weight plus the normal force, and that's just going to be minus mg ez plus n. And so we use plus n, minus mg ez because upwards is the positive z direction and the weight points downwards. And so for the normal force, we know that the normal force is going to be perpendicular to the surface that's defined. So we have that z equals minus r squared square rooted, and so we know that it's going to be perpendicular to the surface defined by, so minus z minus r squared equals 0, and we'll call the left hand side of this equation f of z and r. And so what we can say is that our normal force is just going to be proportional to the gradient of f, because the gradient of f is a vector that's normal to the surface, right? It's normal to the surface that's defined by this equation. And so we can compute the gradient of f, because the gradient of f is just, so gradient of f is just df by dr, pointing in the r direction, plus df by dz, pointing in the z direction. There's no theta term because in our expression for f we have no theta appearing. And so df by dr, so df by dr is just going to be minus, so 2r, minus 2r over 2 times square root r squared minus little r squared. That's just going to be r over r squared minus little r squared, square rooted, and so df by dz is just minus 1. So our gradient, so grad f, is just r over r squared minus r squared, square rooted, pointing in the r direction, minus 1 pointing in the ez direction. And our normal vector, so our normal force, is just going to be, so n is just going to be the magnitude of n times the vector, the unit vector that's normal to the surface. And the unit vector normal to the surface is just going to be given by the gradient of f divided by its norm, right? And so the norm of the gradient of f is just going to be, so r squared plus 1 over r squared minus r squared, all under this big root. And so that's just going to be, so r squared plus capital R squared minus little r squared is just going to be r over square root r squared minus r squared. And so that's the norm of the gradient. So we can just write that this square root is just minus z, and so it's this one. And now we have an expression for our normal force. So know that our normal force is just going to be n times minus z over r times, so r over minus z, pointing in the r direction, and then we'll have plus z over capital R, pointing in the z direction, times n. And so we see that that just becomes, so let me just add new page. And so we see that that will just become that n is just n times r over r, er, plus n times z over r, ez. And so that's our expression for the normal force. And we see that now we have an expression for a normal force, and we can now write our Newtonian equations for the r, theta, and z components. So let's carry out this calculation. So we have the acceleration, so m r double dot minus r theta dot squared is just going to be the r component of our normal force. So it's going to be n times r over r. And then for the theta we have m times, so r theta double dot plus 2r dot theta dot. That's going to be equal to 0 because none of our forces are acting in the theta direction. And then we have our last equation for the z. So m z double dot is going to be minus mg, so the weight, plus the z component of the normal force. And so the z component of the normal force is this. So it's going to be n times z over r. So these are the Newtonian equations for the motion of the bead. So now we can look at the next question. And so in the next question, we're being asked to eliminate, so let me highlight this. So we want to eliminate z and the constraint force to get an equation for r and theta. So what we can do is let's label these equations. So this will be equation 1, this will be equation 2, this will be equation 3. And what we see is that if we take equation 3, so we take equation 3, so sorry, this is going to be question 2. So if we take equation 3 and we multiply it by minus little r over z, so times minus r over z, and we add it to 1, we see that these, so let me use the crayon, so we'll see that these two terms are going to get cancelled out. So let's do it. So we have that, so m r double dot minus r theta dot squared minus m r over z times z double dot is going to be mg r over z. And so we can divide everything by r, and we get that r double dot minus r theta dot squared minus r over z double dot equals gr over z. And so in the next part of the question, they were asking us to also eliminate z. And how can we eliminate z? So we know that there's a constraint on z. The constraint on z is that z is minus r squared minus r squared. And so we can use this to find z dot and z double dot. So we see that z dot is just going to be r dot times d by dr of the square root. So d by dr of minus r squared minus r squared square rooted. And that's just going to be r over square root r squared minus r squared times r dot. And we can do a similar thing to get the acceleration. So z double dot is going to be, so r over r squared minus r squared times r double dot. And then we have to pull a factor of r dot and another r dot, so we'll have an r dot squared times, so we'll have r squared minus r squared times, so r squared over root r squared minus r squared, all divided by r squared minus r squared. So I'm just using that u over v prime is just u prime v minus v prime u over v squared. I'm just using this rule. And so we see that in this case, we see that, so z double dot is just r over square root r squared minus r squared times r double dot plus, we'll get an r squared on the numerator, and then we'll get a r squared minus r squared to the 3 halves times r dot squared. And so this is our expression for the acceleration. And so what we can now do is we can insert this into our equation. So therefore, we get that r double dot minus r theta dot squared plus, so let's look at what we have. We have a minus r over z, so that will become a plus because z is minus some square root, so z is minus this square root. So we'll have plus r squared over r squared minus r squared times r double dot, and then we have a plus, so this will be a r squared over r squared minus r squared whole squared times r dot squared, and that will just be equal to gr over r squared minus, so minus gr, right, because z is minus square root. So we can keep manipulating this equation, and we see that we can clump up the r double dots together. So we'll have that, so 1 plus capital R squared over r squared minus r squared times r double dot, oh sorry, this should be a little r, so little r squared, then we'll have a minus r theta dot squared plus r squared over r squared minus little r squared whole squared times r dot squared plus gr over r squared minus little r squared square rooted is equal to 0. And this term can be simplified, and we see that we have capital R squared over capital R squared minus little r squared times r double dot minus r theta dot squared plus r squared over r squared minus r squared whole squared times r dot squared plus gr over r squared minus little r squared square rooted equals 0. And so this is our equation for r and theta. Good. Now, in the third question, we're asked to find a conserved quantity. And if we look at the equations of motion that we have, so I think it was on this page, we have that the equation of motion for theta is just this equals 0. So let me rewrite that. So we have that, so question 4, so we have that r theta double dot plus 2 r dot theta dot equals 0. And so the trick here is to rewrite the left hand side as the 1 over r times the derivative with respect to time of r squared theta dot, because if we expand this, so that would just give us, so 2r r dot theta dot plus r squared theta double dot, which is correct. And if we divide it by r, we'll get this expression again. And so since it's equal to 0, so we have 1 over r d by dt of r squared theta dot equals 0. We can bring in a factor of m again, so we can write that 1 over r times d by dt of mr squared theta dot equals 0. And so we see that that means that our m r squared theta dot is a constant, and this quantity is the angular momentum. So we found a conserved quantity from the equations of motion. So now if we look back at our question, we're asked to use this conserved quantity to show that the equation of motion for r alone is of this form, where we have c is some unknown constant. So let's try and see how we can do this. So we have the angular momentum is conserved. So what we can write is that, so m r squared theta dot is just some L for the angular momentum. So that means that theta dot is just L over m r squared. And remember, in our equation, in our equation of motion, we had this term appearing. And so we can rewrite this equation by inserting our factor of m r squared, L over m r squared, or angular momentum. So we would just get that r squared over capital R squared minus little r squared times r double dot minus r times phi dot squared. So minus r times L square over m square r to the 4 plus, what do we have? We had r squared over r squared minus r squared whole squared plus times r dot squared plus gr over big R minus little r squared square rooted equals 0. And if we go back and look at what they give us, we see that we get exactly something of the form, right? We get that. In fact, what we see is that what we can do is just remove this r and turn this into an r cubed, and we see that c equals L squared over m squared. So let's look at the next question. In the next question, we want to find the speed v0 at which the bead will move in a circle of radius r0. So if the bead is moving in a circle of radius r0, so let's look. So this is question 5. So if r is just r0, then r dot equals r double dot equals 0. So you can just go back to our equation and replace r dot and r double dot with 0 and r with r0. So we just get that. So basically what we end up seeing is that this term and this term vanish. And so we get that. So we get that g r0 over r squared minus r0 squared square rooted equals L squared over m squared r0 cubed. So what we can do is rearrange this expression to get a result for L, for the angular momentum, and from there we can find the speed v0. So we see that this implies that L squared is just g m squared r0 to the 4 divided by square root r squared minus r0 squared square rooted, and we just see that m squared v0 squared times r0 squared is equal to g m squared r0 to the 4 over r squared minus r0 squared square rooted. So we can divide by m and r0 squared, and we just get that v0 squared, so v0 is just going to be g r0 squared over r squared minus r0 squared square rooted, all square rooted. So v0 is just r g to the half over r squared minus r0 squared to the 1 over 4. This is our expression for the velocity at which the bead will move if it's in a circular orbit. So in the last question, we want to find the frequency of small radial oscillations around the circular orbit found in the previous question. So to find the frequency of small radial oscillations, what we have to do, so let me add some pages. So what we want to do is we want to essentially assume, so we want to say that our R is just going to be R naught plus epsilon, where epsilon is very small, right? A small deviation from the circular orbit. And we can just write that R dot is epsilon dot and R double dot is just epsilon double dot, and we can insert this into our equation. And what we want to do is essentially keep the terms, so we want to Taylor expand our equation and retain only the linear terms. So we Taylor expand the equation keeping the linear terms in epsilon. And if we do that, we could hopefully obtain an equation for simple harmonic motion. So let's look back at our equation. So it's this one. And so let's rewrite it and Taylor expand it. And so first of all, we notice that this term will disappear because we only want the linear terms in epsilon. So what we end up with is, so we have R squared plus R naught plus epsilon squared. Sorry, this should be a minus. This one times epsilon double dot. Here we have minus L squared over M squared, R naught plus epsilon cubed. Now we have plus G R naught plus epsilon over R squared minus R naught plus epsilon whole squared square rooted. So we have to linearize this equation. So what we could start to do is approximate the different terms. So we see that in this denominator, we're going to have to approximate 1 over R squared minus R naught plus epsilon squared around epsilon equals 0, because we're considering small deviations. And so if we use the Taylor series, that would just be equal to 1 over R squared minus R naught squared. And then we'd have to differentiate this expression. But if we differentiate this expression, we'll have an epsilon on top. And we're only interested in the linear terms in epsilon. So the linear term will be brought by the acceleration, right? Because we'll have plus, so some constant times epsilon on top. But we don't want this term because we only want the linear terms. So therefore we just get that the first term, so let's call this 1. So 1 linearized is just, so R squared over R squared minus R naught squared epsilon double dot. Now let's look at our second term. So in our second term, we have a R naught plus epsilon to the minus 3 that appears, but we can just write this as R naught to the minus 3 times 1 plus epsilon over R naught cubed to the minus 3, right? And so, sorry, this should just be an epsilon on the denominator. It's just be an R naught. And so what we can do is we can use the formula that 1 plus x to the n is about equal to 1 plus nx, right? And therefore this is approximately equal to 1 over R naught cubed minus, so minus 3 epsilon over R naught to the 4. And so the second term linearized is just 3 L squared over M squared R naught to the 4 times epsilon. Good. And now let's look at the third term. So in this third term we have a bit of a more complicated expression. So we have a 1 over R squared minus R naught plus epsilon squared square rooted. So we can Taylor expand this and just say it's approximately equal to 1 over R squared minus R naught squared square rooted plus R naught epsilon over r squared minus r naught squared to the 3 halves. So I'm just differentiating this and evaluating it on. I'm just differentiating this expression for epsilon equals 0 and evaluating it at r naught. And so therefore we see that we can approximate our third term. So a third term just becomes, so we'll have a g epsilon over the square root plus r naught squared, so g r naught squared epsilon over r squared minus r naught squared to the 3 halves. And so we can multiply this side over there by r squared minus r naught squared to the 1. So we just get that g r squared epsilon, because the r naught squareds will cancel, over r squared minus r naught squared to the 3 halves is the linearized term. So now we have a linearized equation, right? So we can just do 1 plus 2 plus 3, and that's just going to be equal to r squared over capital R squared minus r naught squared epsilon double dot, and we have this term, so we have a 3 L squared over m r naught to the 4 plus gr squared over r squared minus r naught squared to the 3 halves times epsilon equals 0. So this equation starts to resemble simple harmonic motion, but before we carry out the calculation, we should remind ourselves that we found an expression for L squared. This expression was on the previous page, so I think it was somewhere here. Yeah, so it's this expression. And so we see that the m squares and the r naught to the 4 cancel out, and we get that this is just, so we get r squared over r squared minus r naught squared epsilon double dot plus, now we get 3g, so this should be an m squared also, so we get 3g over, so I think it should be a square root, 3g over square root of this r squared minus r naught squared plus g r squared over r squared minus r naught squared to the 3 halves times epsilon equals 0. And what we can do is we can just multiply this equation, this part, by r squared minus r naught squared, and so we just get that, so r squared over r squared minus r naught squared epsilon double dot plus, so now we'd have 3g r squared plus g r squared, so that would be 4 g r squared minus 3g r naught squared, so I'm just making everything under the same denominator, times r naught squared minus, capital R squared minus r naught squared to the 3 halves, epsilon equals 0. And so we see that the we see that we have an expression. We see that we find that so let me just insert page. We see that we're left with an expression that says that the acceleration epsilon double dot plus some constant times epsilon equals 0, and this is simple harmonic motion. And so the frequency is just given by omega naught equals square root of c. And so all we have to do is divide this by, divide everything by r squared over r squared minus r naught squared, and so we see that we get the following expression. So we get that 4, so we get that c equals 4 gr squared, 4g r squared minus 3g r naught squared, and then I have to write r squared square root r squared minus r naught squared. And so therefore our omega naught is just this square rooted, right? So it's just going to be 4g r squared minus 3g r naught squared over r squared square root r squared minus r naught squared, all under this big square root.